In this lecture, I'll go over the two methods for the synthesis of ethers, and then we'll go over the reaction of ether. So the first method to make ethers is by Williamson synthesis. This is the best method to synthesize ethers, and it is a two-step reaction. To make an ether, what you need is an alcohol. So you always start with an alcohol, and you start with an alkyl halide. You combine those together in there by a two-step reaction. So the first step, you take the alcohol and you react it with a base. Now the base that you are going to use, as we mentioned, needs to be a strong base so that it can take the acidic hydrogen and make the alkoxide. So the first step in the Williamson synthesis is an acid-base reaction. This is the first step. Now once you make your alkoxide, then you're going to take that alkoxide and react it with a primary or a methyl alkyl halide. The reason why we want to do this because the second step is a simple SN2 reaction. If we start with a secondary alkyl halide, then you're going to end up getting your elimination product as well, because after all, this is going to be a strong base. So you don't want an E2 elimination product, you just want the substitution of product, which is the ether in this case. So this is why you have to limit your alkyl halide to a primary or a methyl halide in there. Don't use a secondary. If you use a secondary, you will get the ether, which is the SN2, but you will get the E2 byproduct with it. And of course, if you start with a tertiary alkyl halide, we know that substitution SN2 does not happen with a tertiary alkyl halide, but elimination will. So you're not going to get the ether, you're just going to get your E2 product. Let's say, for example, I want to go ahead and synthesize this ether. So the first thing that you would need to do is locate the bonds that you can go ahead and break. Because after all, ethers are made by reactions of alcohols and primary alkyl halides. It's either a primary alkyl halide or a methyl alkyl halide. Okay, so I want to pick from that ether a side which is an alcohol and a side which is an alkyl halide, precisely a primary alkyl halide in there. So we're going to go ahead, we have two routes to go with and two bonds that we can break. Let's see which one is the best. So we can break this bond between the carbon and the oxygen. And if we break this bond between the carbon and the oxygen here, so if we break it, then in this case, this whole thing is going to be my alcohol part. And this whole thing here, it's going to be my primary alkyl halide. Now, since it is a primary alkyl halide, all I did here is I will stick a halogen to this carbon and I will stick a hydrogen to this oxygen here. Since this end is a primary alkyl halide, this route can go and I can synthesize this ether by the alkyl halide and the alcohol. So let's go ahead and write both the alkyl halide and the alcohol. So step number one in this reaction, I will start with the alcohol always. So for the alcohol over here, you're going to end up just adding your OH, in there. Keep the same number of carbons, and you're going to react this with a base. Any strong base can do the job. This is the hydride in here. So the hydride is going to come act as a base, come take the acidic hydrogen and form the alkoxide as usual. This is a simple acid-base reaction. Now the alkoxide, this one is going to be our nucleophile. So in the first step, you made the nucleophile that you want to use in the second step of the SN2 reaction. So in step number 2 in here, I'm going to go ahead up here, and this is going to be my alkyl halide. So the alkyl is going to be made up of two carbons here. So I'm going to use those two carbons. It's a CH3, it's a CH2, And then I'm going to go ahead and stick a halogen to that. And the halogen is going to be a chlorine or a bromine or an iodine. Any one of those can do the job. Don't be general, so be specific. So don't just put an X in there. Be specific with the halogen. And now this one, we're going to go ahead and react it with the alkoxide. So reacting this with the alkoxide over here, this is going to go with an SN2 reaction because this is a primary alkyl halide, and this one is a strong nucleophile. So the reaction is going to come and go with an SN2 reaction. The nucleophile is going to attack the electrophilic carbon, the halogen is going to leave, and you're going to end up simply making your ether this way. So you're going to end up having the ether. So I have 2 carbons on the side. These 2 carbons are these 2 carbons. And then the ones that belong to the alcohol are the oxygen, the carbon, and the isopropyl group. And this one is the oxygen, the carbon, and the isopropyl group in there. So notice that the ether is divided into 2 parts. It's divided into an alcohol part and an alkyl halide part. So during the process, I lost the hydrogen from the alcohol and the halogen from the alkyl halide. So I lost an HX in there. This is one route I can go with and make my ether. Another route is I can go ahead and break this bond. Let's go ahead and write that same reactant again. So this is it. So that same reactant again. And this is the other route. I can go ahead and break this bond now. So breaking this bond is going to make this part an alcohol. Okay. Because the oxygen is connected to it. So this is why it's an alcohol. And this part over here, it's going to be our alkyl halide. So our alkyl halide is going to be a halogen here. Any halogen, chlorine, bromine, or iodine. So, and it's still a primary alkyl halide, so the reaction can work. So for the Williamson synthesis steps, let's go with the step number 1. I'm going to start with my alcohol, and I'm going to react it with the sodium hydride, negative charge. So this is going to come, take the hydrogen, form a negative charge on the oxygen. This is going to be my nucleophile, which is the alkoxide there, balanced with the sodium. And then the second step, step 2, I am going to take my alkyl halide that I have here. So all what you need to do is just to stick a halogen there. Here you go. Pay attention to the number of carbons. Here I do have 4 carbons. So please count your carbons. And I'm going to react it with my alkoxide. At the end, you need to end up getting the same ether that you want to synthesize. So this is going to come, it's going to attack the carbon of the halogen. And as I said, just be specific. So instead of the X, we're going to go ahead and write, for example, a bromine. And the bromine is going to leave. This is an SN2 reaction. It's a strong nucleophile. You can use a solvent, which is a DMF solvent or acetone, any polar protic solvent, aprotic solvent, can do the job. And your product in this case is going to be, so I have, this is going to be the part of the alkyl halide. I added to that my part of the alcohol in this case, and this is the ether. So both ways are good ways in order to make the ether. I can simply break this bond, or I can break this bond for this particular example, because in both ways I can have a primary alkyl halide. Now, in one of the steps, if you end up getting a secondary alkyl halide or a tertiary alkyl halide, then the reaction cannot happen. Another example here, you want to make this ether. So we have 2 routes, either breaking this bond or breaking this bond in there. So if we want to break this bond over here, then this part is going to be our alkyl halide, which is going to be primary. And the whole thing is going to be our alcohol. We can do this because it's a primary alkyl halide. But if we break this bond, this one is going to be the alcohol, which is fine, but this here is going to be our alkyl halide. We're going to stick a halogen to it. We know that SN2 cannot happen with an sp2 hybrid carbon. SN2 happens with an sp3 hybrid carbon connected to the halogen. So this means that this route, path 2, cannot happen. So only we need path 1 in order to make that ether. Now let's say, for example, if I have my alcohol and my leaving group within the same molecule. Okay, before the alcohol and the leaving group, they were in two different molecules, and I combined them together using a base. Here I am having my alcohol and my leaving group in the same molecule, and I am reacting this in presence of a base. Now we all know the rule in here and what the base does. So the base is going to come and take the acidic hydrogen. Where is the acidic hydrogen? The acidic hydrogen is simply this hydrogen over here. So the acidic hydrogen is this hydrogen over here. So the first step is that the base is going to come and take the acidic hydrogen and form a negative charge on the oxygen. So you're going to end up having your oxygen here. Count your carbons. I'm not adding any additional carbon in there. I have 1, 2, 3, and 4 carbons. This is 1, this is 2, this is a 3, and this is 4 carbons, and this is a bromine. So what did I create over here is an alkoxide. Still, I am working with the Williamson synthesis, but the difference is that the alcohol and the alkyl halide, they are in the same molecule instead of being in separate molecules. And this mechanism is called an intramolecular Williamson synthesis instead of a regular Williamson synthesis. Now, here I'm having my alkoxide, which is the nucleophile. And here I know that this carbon is going to be my partial positive carbon in there. This is the electrophile. So you have a nucleophile and electrophile. By definition, if you are in a longer chain, the nucleophile can attack the electrophile if the nucleophile is not far away from the electrophile by more than 5 carbons. So here the nucleophile is far away by 1, 2, 3 carbons in there. So yes, the nucleophile can attack. But if the nucleophile is far away by more than 5 carbons, it will be very far away. It won't reach the electrophile in there. So you have to close the cycle from 2 carbons up to 5 carbons max between the nucleophile and the leaving group. So your nucleophile over here is going to come and is going to attack the carbon, and the bromine is going to leave. So what did I do over here? I made a bond between the oxygen here and the carbon here. Okay, so I'm going to close the cycle. Always the product in the intramolecular Williamson synthesis is a cyclic ether, not a regular ether. It's going to be a cyclic ether. So to draw the cyclic ether, I'm just going to go ahead and number my carbons starting from the oxygen now. So it's going to be 1, 2, 3, 4, and 5, because after all, I'm making a bond between carbon 5 and oxygen 1 in there. So I have a cycle of 5-membered rings. As simple as that, make it easy. Draw your 5-membered rings in there, and put the oxygen on one of the carbons, and this is going to be number 1. You can number from this side or number from the other side. It really doesn't matter. Just pick a side and number. And this is going to be number 2, number 3, number 4, and number 5. So what you did here, you made a bond between carbons 5 and oxygen 1 in there. And that is going to be your ether that you formed, plus your Br minus in there that left, and that Br minus, of course, is going to couple with the sodium that is in the solution. There are additional examples in the notes here about intramolecular Williamson synthesis. And again, in order for the cycle to close, you should have a separation between the nucleophile and the leaving group by not more than 5 carbons. Okay, we're talking about carbons, not including the oxygen. So here the separation is 5 carbons. It's 1, 2, 3, 4, and 5, and this is the max. For example, if we have something like this over here, so notice here, if we have something like this is so far away. So if we create the alkoxide, your nucleophile is so far away from the electrophilic carbon. So there is no way that the nucleophile will reach that far to kick out the bromine. So the cycle will not close. On the other end here, the cycle can close because the nucleophile here is close to the electrophilic carbon, which is carbon number 5. In there, so the cycle can close. Put this as a note that the max that you can form is a cycle of 6-membered rings. Here I'm forming a cycle of 5-membered rings. And when I say membered rings, I'm counting every single element in the cycle. So this is a 5-membered ring. I can form a max of a 6-membered ring, something like this. This is a 6-membered ring in there. When you have, if you look at this example in here, you need to number because sometimes you have substituents on the chain so that you know exactly where to put the substituent. Another way to make ether, and this method, they use it in industry, is to condense two alcohols together. However, the alcohols that you are condensing together need to be very small alcohols. So they shouldn't be branched alcohols. They can be either 2 methanols or 2 ethanols or 2 propanols. That's it. You cannot combine 2 alcohols together. This reaction happens in presence of heat and an acid. And all what you're doing here is that you are losing an OH from one of the alcohols and the hydrogen from the other. This is why we call this reaction a dehydration reaction, because you are losing water, an OH and the hydrogen, and you are making an ether in this case. So after considering the synthesis of ethers, how to make ethers, let's consider the reaction of ethers. It's only one reaction that we will consider in this chapter, which is the cleavage of ethers in presence of an acid. And the acid is either HBr or HI. So you start with an ether in there, and the sigma bonds are going to be broken in there. So you choose the CO bonds and you break those CO bonds in there. The cleavage of the CO bonds is going to depend on the type of the R group that is connected to the oxygen. So if the R that is connected to the oxygen is a primary, then the cleavage on that side of that R is going to go by an SN2 reaction. And if the R that is connected to the oxygen is a secondary or a tertiary, then the cleavage on that side is going to go by an SN1 reaction. In this case, and in this case only, substitution SN1 and SN2, they happen in the same reaction, but they will not happen together. Always SN1 happens before SN2. So the reaction, if you have SN1 and SN2 together, always the reaction starts with SN1 and continues with SN2. So SN1 and SN2 are not going to happen simultaneously. And so how the reaction is going to look like. Let's consider this example here where we have an ether. The ether here is not symmetrical. This means that the R groups are different from both sides. So the first thing that you would need to look for is the R groups that are connected to the oxygen, and precisely you need to look for the carbons that are connected to the oxygen and evaluate what type of carbons they are, because this is the mechanism going to be of the reaction. So this R over here, it's a primary R group, and this R over here is a secondary R group. So this mechanism, the cleavage of this CO bond is going to go by an SN2 reaction, and the cleavage of this CO bond is going to go by an SN1 reaction in there. The reaction is going to proceed by breaking both bonds and sticking a halogen to each end of the carbon. The reaction happens in excess of the HX because you will be using HX twice, and every time you use the HX, you're going to break a sigma bond in there. This is why we have an excess HX. This is going to be the general reaction in there. Let's go ahead and consider the mechanism. So you're going to start with the most substituted side first. And you're going to start with the SN1 mechanism first. So you take your ether in there and you react it with the first mole of HBr, which is acid. So here my medium is acidic, and you have an oxygen, and you know that this oxygen is my basic site. So the first step in this reaction is going to be an acid-base reaction. You want to protonate this oxygen to start the SN1 reaction, and we know that the SN1 reaction cannot happen if we don't have a good leaving group. The OR is not a good leaving group. The OR is a bad leaving group because when it leaves as a strong base, not as a weak base. So this is why to make the oxygen a good leaving group, we have to protonate it. And to protonate it, this step is essential. This is why I'm using the acid. So you add in the acid, you protonate the oxygen, you introduce a plus charge to the oxygen, and now this guy over here is going to be a good leaving group because when it leaves in a form of a weak base. So it is a good leaving group. So now I can start my SN1 reaction. So we already know that SN1 is 2 steps, and the first step requires the leaving group to leave, and then the second step requires the nucleophile to attack. So the leaving group is going to leave, you're going to make a carbocation, and then the nucleophile is going to attack. So where is my nucleophile here? Of course, the nucleophile is not whatever left, because if this one attacks, it's as if you did nothing, you're going to go back to whatever you start with. The nucleophile is from the acid itself, because here what I'm using is HX. X is my nucleophile, but the nucleophile here is not free. It is connected to the hydrogen. So this is why my first step required the protonation. I took the hydrogen away and I released the nucleophile. Now the nucleophile is ready to react with the carbocation. I cannot rearrange that carbocation in there. It is not a chiral center, so this is going to proceed by just the attack on the positive charge, no racemization, and I'm going to get my first product in there. It's going to be the first product and whatever left from the other part of the molecule, which is here. It's this one that I'm going to take and proceed with my next step in the reaction. And the next step in the reaction is simply reacting this by another mole of HBr. So this is going to be now the cleavage. This part is going to be the cleavage by SN2 reaction. So we're going to take this and we're going to protonate it because every time we have an oxygen, this is a bad leaving group. So we have to protonate, make it a good leaving group so that SN2 can happen. And the bromine is going to leave. Now I freed my nucleophile. Now water is an excellent leaving group. So this guy over here is a very good leaving group. So the bromine is going to come, it's going to attack by an SN2 mechanism. It is a one step. The bromine attacks, water is going to leave, and you're going to end up getting your second product. So the overall product are these two products in there. So let's go ahead and consider another example here. We got to pay attention to the R group that is connected to the oxygen. Because if the R group is an sp2 hybridization, there will be no substitution on that side in there. So that side will remain a phenol. And the other side, you can cleave it and you add a halogen to it. After all, in these reactions, whenever we have these reactions, in there and you want to write the product, you're going to cleave both sigma bonds that are connected to the oxygen, and you're going to stick a halogen on each carbon that is connected to the oxygen in this case. So you're going to end up getting two products. But if you have an sp2 hybrid carbon, you cannot do that on the side. So that side of the sp2 hybrid carbon will remain the same, and it will change into an alcohol. It will be an alcohol, no matter what alcohol that is. It will be an alcohol. It will not change into an alkyl halide. The other side, you can simply do a cleavage on. This is going to be an SN2 cleavage here that you can have, but SN1 cannot happen in here. So let's go ahead and do the mechanism of the reaction. First step, you're going to go ahead and you protonate the oxygen. So this is going to be your oxygen over here. And that is going to come, attack the acidic hydrogen, and iodine is going to leave. So you are protonating the oxygen, and this is going to be the first step of the reaction in there. Now, the second step is that you're going to use the I-, right? And the I- is going to come and attack, but the I- cannot attack here to allow this whole group to leave. You cannot start by the SN1 reaction because there is no SN1 reaction in there. So the I- instead is going to come and attack this carbon instead and have everything leave. And there, remember that SN1 cannot happen whenever you have an sp2 hybrid carbon. SN1 happens only with sp3 hybrid carbons. SN2 happens only with sp3 hybrid carbons as well. So this is my only sp3 hybrid carbon, and this side is the primary R. So this is why the I- now, it's going to come and attack this carbon and allow everything to leave. Okay, and you're going to end up getting your product where the reaction is going to stop here. Nothing is going to happen because you cannot protonate this oxygen, because even if you protonated this oxygen, the water is not going to leave because this is again an sp2 hybrid carbon.